Welcome. We have started the module on cost diagram, and today we shall see a tutorial on it. In the past 3 lectures, we studied various aspects of cost diagram as how we can convert basic flow sheet into an energy integrated flow sheet. So, the cost diagrams were prepared by putting the cost information right onto the flow sheet. The annualized capital cost of the equipment was put inside the box that indicated the particular equipment, and the processing cost was allocated to a particular stream. A complicated cost diagram of an energy integrated hydrodealkylation process of toluene was converted into a relatively simple diagram of the what we called as the lumped cost diagram. Lumped cost diagram was prepared by identifying the cost intensive operations in the flow sheet and then summing up the cost, that is cost of the equipment that is involved in each of these operations. So, these operations were the feed and recycle heating, reactor, product cooling, then gas recycle compressor and separation of the 3 liquid streams benzene, toluene and xylene through 3 columns, stabilizer column, benzene column and toluene column. Then we distributed the cost of the common equipment to the 2 processes depending on the contribution of that particular process. Like for example, the major distribution was for the cost of heat exchangers, okay, and then the cost of heat exchanger was distributed in the inverse proportion of the film coefficient of the 2 streams that were involved in that particular exchanger, because the cost of heat exchanger is proportional or varies with the area of the heat exchanger. Thereafter, we converted this lumped cost diagram into cost allocation diagram, in which we distributed the particular cost for each operation to the 3 streams that were involved in the operation. Those were called as cost elements. Okay. Now, cost elements were 3. First, the net fresh feed, which is the sum of the gaseous feed, that is hydrogen plus impurity of methane, and also the toluene liquid feed. Then the gas recycle stream, which contained 40% hydrogen and 60% methane typically, and then the liquid recycle stream. Okay. And then we arrived at the cost allocation diagram that you see on the screen now, and thereafter we evaluated using this cost allocation diagram various process alternatives. What were the process alternatives that we had? At level 2 input output structure of the flow sheet, we had the alternative of purifying the hydrogen feed stream. Then we had the alternative of recovery rather than recycle of the diphenyl. Then the use of gas recycle and purge stream. Thereafter, at level 3, the recycle structure of flow sheet, we had the option of using a single reactor, use of a recycle stream for unreacted reactant. Then the third design variable that we had, a major design variable, that was the molar ratio of the 2 reactants, hydrogen and aromatics, at the reactor inlet. Then the recycle gas compressor, then the mode of reactor operation, whether adiabatic or isothermal, and finally the equilibrium limited reactions, the shift of the equilibrium to favorable side. Now, in hydrodealkylation process, diphenyl is a reversible byproduct. So, shifting the equilibrium to benzene side is a favorable shift, and we saw how we can achieve it, or what are the consequences of recycling diphenyl, that also were assessed in the last lecture. Now, in this lecture, we shall see various energy integrated options of the hydrodealkylation process. What we saw in previous lecture was just one option that you see on the screen now, okay, but there could be many alternatives, and today we shall analyze the cost diagrams of these energy alternatives, and moreover we shall also prepare a cost allocation diagram for one of these alternatives. So, let us see the first problem, okay, the problem of preparing the cost diagram for different energy alternatives. We are given 4 figures that show alternative flow sheets for energy integration for hydrodealkylation process to hydrodealkylation process of toluene to produce benzene. The figures indicated inside the equipment boxes of the flow sheet are annualized capital cost in $1000 per year, and the numbers written outside the equipment box indicate the annual cost of the utility that is cooling water, that we have indicated as C/W, or steam indicated as STM, or fuel for the furnace, or power for the compressor associated with that particular equipment, and the operating cost is also in $1000 per year. We are given a table that gives the film transfer coefficients of various streams in the different flow sheet corresponding to the figure number. Let us first see the flow sheets that we have. The first flow sheet is on your screen. Here we have a reactor, the effluent stream first passes through FEHE, feed to effluent heat exchanger, thereafter it goes to water cooler. So, here we have only one FEHE, and then the fresh feed is heated through FEHE and a furnace. Here we see a recycle of toluene and diphenyl. Okay, so there are only two columns, and what you see are the numbers corresponding to the annual capital cost. Then the second alternative. In the second alternative, there are two feed to effluent heat exchangers. The effluent stream from the reactor enters the second exchanger first, then it drives the reboiler column of the stabilizer column. It drives the reboiler of the stabilizer column, then it enters the first feed to effluent exchanger, thereafter it enters the final water cooler, and thereafter the flash drum. Okay. And the feed and recycle hydrogen and toluene are heated through the two exchangers as well as a furnace. So, that is the second alternative for the energy integrated flow sheet. The third alternative is now on your screen. Here we see that the benzene column reboiler is being driven by the reactor effluent. The stabilizer column has been given separate steam for the reboiler. Okay. Rest of the flow sheet is more or less similar. Okay. And finally, the fourth integrated flow sheet is that the reactor effluent first enters the second FEHE, thereafter it drives the reboiler of stabilizer column, thereafter it drives the reboiler of benzene column, thereafter it goes into FEHE1, the first feed to effluent heat exchanger, and finally into water cooler. So, we have to prepare the lumped cost diagram for these four flow sheets, and we are given the film transfer coefficients for each of the streams. Okay. Now, let us start with the first flow sheet. Preparation of lumped cost diagram. The operations that we have: cost components, or the operations for which we shall list the cost, are first the reactor, then the feed and recycle heating, the product cooling, then the two columns, and finally the gas recycle or recycle compressor. So, these are our cost components, and we shall now lump the cost for each of these components. Okay. Let us start with figure 1. Okay. Here we have only one feed to effluent heat exchanger, whose capital cost we have to distribute between the two streams that it is treating. The stream 1 is the reactor feed and the stream 2 is the reactor effluent. We are given the heat transfer coefficients as 0.69 kilowatt per meter square per Kelvin for reactor feed, and again 0.69 kilowatt per meter square per Kelvin for reactor effluent. Yes, so we have to distribute that cost, and since the coefficients are same, the cost will be distributed equally. Okay, that point we note. Figure 1. Only energy integrated exchanger is FeHe1, okay, cost divided in proportion of inverse of the film coefficient that we denote by H of the process stream involved in it. Stream 1 in the exchanger is reactor feed. The coefficient Hi is 0.69 kilowatt per meter square Kelvin. Then the second stream, stream 2 is reactor effluent. The film coefficient is 0.69 and the cost is divided half in $1,000. Okay. So with that we collect the cost associated with each of the given component. First, the feed and recycle heating. Now feed recycle heating takes place through FeHe1 and the furnace. So those two things we add. The furnace cost 65 plus 200, fixed cost and operating cost, plus the portion of FeHe, and the total cost is thus 285. Then the product cooling. Product cooling occurs through FeHe1 as well as the condenser. Condenser has annualized capital cost of $20,000 and cooling water cost of $40,000. So those two things we add. 20 plus 40 for water cooler plus the portion of FeHe1, and then the total is 80. Then the third is the reactor. Reactor has the total cost of 200 that we take as it is. Then the recycle compressor. The recycle compressor has $50,000 as the annualized capital cost and $60,000 of power. So those two things add. 50 plus 60, 110. Then the stabilizer column. For the reboiler, for the $15,000 is the annualized capital cost of the reboiler and $30,000 for the steam required for it, and then the cost of column itself $25,000. So this together adds up to 70,000. Then benzene column. $20 plus 45 for the reboiler, 20 plus 45 for reboiler, then 20 plus 50 and 20 plus 10 for the two condensers, and 75,000 for the column itself. This together comes out to be 240. And then if we put all these numbers in the boxes, we get the lumped cost diagram for that particular flow sheet. We are now connecting these boxes. Each box indicates a particular operation. Now we have not been given any information about the cost of recycle and purge, so that is not indicated here. We are now putting different numbers. $200,000 capital cost, annualized capital cost of the reactor, $110,000 for gas compression, $285,000 for feed and recycle heating, $240,000 for benzene column, $70,000 for stabilizer column, and $80,000 for product cooling. And this completes our lumped cost diagram for process alternative 1. Now we can proceed similar way for the other diagrams. Now I will go a bit fast because I have already explained in detail. We have to follow a very similar procedure for the other flow sheets. Okay. Now let us take flow sheet 2. In flow sheet 2 we have 3 energy integrated exchangers, FEHE1, then FEHE2 and the reboiler of the stabilizer column. So we have to distribute the cost according to the film coefficients of the streams that are involved in each of these 3 exchangers. Okay. So that point we note now. Figure 2, cost distribution for energy integrated exchangers, FEHE1, FEHE2 and stabilizer reboiler. And then streams involved: feed, effluent, reactor effluent. Okay. Then we are given the HI, heat transfer coefficient, 0.69, 1.57, 0.69, then the allocated cost, then stream 2, for FEHE1 stream 2 is reactor effluent, second also reactor effluent, and for the third it is the stabilizer bottom. The film coefficients are 0.69, 0.69, 1.57, and then the cost. Okay. The total cost of FEHE1 is $40,000 annualized capital cost. Since the two coefficients are same, we distribute equally. Then for the second FEHE2, the total cost is again 40, but the stream coefficients are not same. Feed has higher coefficient, so lesser cost, and that we have already seen how to do it. It is in inverse proportion of HI. So now I write directly the answer. You can very easily calculate it yourself. Low coefficient, high cost, 1.1 divided by 0.69 divided by 1 divided by 0.69 plus 1 divided by 1.57 into 40 is what is 28. Okay, so like that. Then similarly for the stabilizer column, the total annualized capital cost is $15,000. Okay, that is distributed in inverse proportion of film coefficients. High film coefficient, low cost. So 0.69, 1.57 is gives the distribution 5 and 10. Now having done this, we now collect the cost associated with each of the operation. Cost collection for each cost component. Now I am giving directly the answer, you can verify yourself. Feed and recycle heating 65 plus 200, furnace this 12, FEHE2 plus 20, FEHE1, total $297,000. Then second, product cooling, $20 plus 40 for the water cooler plus 20 for FEHE1 plus 28 for FEHE2 plus 10 for stabilizer reboiler. Together it adds up to 118. Next, the reactor. Here we don't have any allocation, so direct $200,000. Then the next one is the recycle compressor. There also the cost remains same as the previous flow sheet. There is no further distribution. 50 plus 60, $50,000 capital, annualized capital cost, $60,000 power, so total $110,000. Stabilizer column, $25,000 for the shell, that is the main body plus the plates, and $5,000 for the reboiler, so total 30. And then benzene column, $20 plus 50 for condenser plus 20 plus 10 the after cooler plus 75 for column shell plus 20 plus 45 for reboiler, and then total gives 240. And now we put all this cost in boxes and then connect them to make the final diagram. Reactor, gas compressor, feed plus recycle heat, product cooling, stabilizer, benzene column, and then we join these things. And now we put numbers: reactor 200, feed recycle heat 297, gas compression 110, product cooling 118, stabilizer column 30, and benzene column 240. And this completes our the lumped cost diagram for the second alternative. Okay. Now I will give the answers directly for the third and fourth, and I leave it as an exercise for you to solve. Okay. Now let me briefly give the description. Here we have, in the third alternative, we have two exchangers, so you have to distribute the cost of the two exchangers plus the benzene reboiler now. Okay. We first see the distribution of cost of energy integrated column. FEHE1, FEHE2 and benzene reboiler. And now I directly give the cost. The total cost 40, 40 and 20, so that is distributed among stream 1, okay, and stream 2. Feed 20, feed 12, bottoms 6, stream 2, effluent 20. Stream 2 is effluent, reactor effluent in all three cases. So for FEHE1, $20,000 is the share of effluent, FEHE2, $28,000 is the share of effluent, and the benzene reboiler, $14,000 is the share of the effluent. Now having distributed this, the total cost for each component or operation. Now I directly give the final figure. I leave the exact breakup to you. Feed recycle heating $297,000, product cooling $122,000, reactor 200, then the recycle compressor 110, stabilizer column 70 and benzene column 181. The same thing in terms of block diagram. And now we put the numbers inside. Gas compression 110, stabilizer column 70, benzene column 181, feed and recycle heat 297, reactor 200 and product cooling 122. So this gives the lumped cost diagram for energy integrated flow sheet 3, okay, or process alternative 3. For the fourth one, I am directly going to give the lumped cost diagram. In fourth alternative, we have 4 exchangers integrated, FEHE1, FEHE2, then reboilers of both columns. So we have to distribute the cost. You have been given the film coefficients in the table. You have been given film coefficients in the table, okay, FEHE1 etc., reboiler of benzene column, reboiler of toluene column. Now you distribute the cost and then finally you can obtain a lumped cost diagram as follows. Reactor 200, product cooling 132, feed recycle heating 297, gas recycle compression 110, benzene column 181 and stabilizer column 30. So this is the the lumped cost diagram for the process alternative 4. Okay. So that completes the first part of our tutorial. Now we have to go further for preparation of the cost allocation diagram. Now as I mentioned in previous lecture, cost allocation diagram is prepared from the lumped cost diagram by allocating the cost of the cost component, reactor and product cooling and feed recycle heating, to the 3 streams that are involved in that particular operation or component. And the 3 streams are net fresh feed, gas recycle and liquid recycle. Now we shall try to prepare the cost allocation diagram for the alternative 2. Okay. Now, we need some more information for that, which now appears on your screen. This is the second problem of our tutorial. Figure 1 shows the general flow sheet of hydro dealkylation process. This we have seen several times before. Okay. This is the general flow sheet indicating various temperatures and the flow of the streams. Okay. Figure 2 shows the energy integrated version of the same. Now, this is what was our process alternative 2, okay, in which we had 2 FEHE and 2 reboiler columns, 2 reboilers integrated. Okay. Now, we have to prepare a cost allocation diagram. The coefficients remain the same as given earlier in problem 1, okay. But however, we have now 3 cost elements: net fresh feed, gas recycle and liquid recycle. Major cost components again are same as before: gas recycle heating, gas recycle compression, feed heating, reactor, product cooling, stabilizer column, benzene column and liquid recycle heating. The process parameters now are reactor per pass conversion 60%, molar ratio of hydrogen to aromatics at reactor inlet 5, composition of hydrogen in purge gas 50%, production rate of benzene 300 kilomoles per hour, selectivity at transient conditions 0.9. However, if you see now the flow sheet, okay, here you will see that the toluene and diphenyl are recycled to the reactor. Therefore, at steady state, the amount of diphenyl in the process remains constant. It builds to an equilibrium level and thereafter it remains constant. And at that condition, at that particular steady state, all of the fresh toluene gets converted only to benzene with selectivity equal to 1. So, selectivity 0.9 is for a transient condition, steady state selectivity is 1 in case of diphenyl recycle. Then equilibrium constant for diphenyl formation 0.24 at reaction temperature, feed gas composition hydrogen 95%, methane 5%. We are given several physical properties: heat capacity in joule per mole per Kelvin, benzene 135, liquid state benzene vapor 82, toluene liquid 156, toluene vapor 104, hydrogen 29, methane 36 joule per mole per Kelvin, all of these heat capacities. Then the boiling points are toluene 110, benzene 80, latent heats benzene 30, in that is in liquid state of course, liquid to vapor state, the latent heat. Benzene is 30 kilojoule per mole and toluene is 32 kilojoule per mole, the heat required for phase transformation from liquid to vapor, that is latent heat. Then the cost data. Toluene cost has been given as $16 per kg mole, benzene $9 per kg mole, hydrogen $1 per kg mole. Fuel cost is $4 per million BTU. I have already given the conversion of BTU to kilojoule. Okay. And the fuel values are hydrogen 0.123 into 10 to the power 6 BTU per mole or 0.123 million BTU, methane 0.383 million BTU. Okay. We are allowed to make certain simplifying assumptions. First assumption is that the phase split in the flash drum is perfect, which means that the gas leaving the flash drum, a mixture of hydrogen and methane, does not contain any vapor of toluene and benzene. Of course, this is not a realistic assumption, but for our initial calculations we can make that particular assumption, because the quantity of benzene and toluene leaving with that particular gas is relatively small compared to the production rates or the rate of the total feed of toluene. Okay. Now, the second assumption is diphenyl in the recycle stream is much smaller than toluene, so ignore the heat duties associated with it, okay, while calculating the heat loads. And the third assumption is that split in benzene column is perfect, with 100% recovery of benzene in the distillate and 100% recovery of toluene and diphenyl in bottoms. Amount of hydrogen and methane exiting from stabilizer column can be taken as negligible. So, with these assumptions and with this data, we have to prepare a cost allocation diagram. Now, we have already made the lumped cost diagram in previous exercise, which is right there on your screen. Okay. And now we start with that particular thing. Let us now write down all the parameters that are given. Parameters for mass and energy balance. Production rate of benzene that we denote by Pb, 300 kgmol per hour. YPH, mole fraction of hydrogen in purge gas 0.5. Molar ratio of hydrogen to aromatic side reactor inlet 5. Per pass conversion that we denote by X is 0.6. Then equilibrium constant KEQ is 0.24 at reactor temperature, and YFH, the mole fraction of hydrogen in fresh gas or makeup gas, is 0.95. Now, with these parameters, I am going to give you the mass balance directly, okay, but you can very easily calculate it. I will give for your convenience the formulae. Okay. FFT, the feed rate of fresh toluene, is Pb by S, but since S is 1, it is equal to Pb. Okay. Then total feed rate of toluene Ft is FFT by X. Then fresh gas is Pb by S into 1 minus YPH into 1 minus S by 2, okay, divided by YFH minus YPH. All of these formulae we have derived in module 2. So, you are supposed to go back to module 2 and revise to see how these formulae have come. Purge gas is fresh gas plus Pb into 1 minus S by 2S. Okay. Rg, recycle gas, is equal to Pb divided by S into YPH into Mr by X minus YFH divided by YFH minus YPH. Now, this formulae we have already derived. We are simply going to put these numbers into this formulae and then obtain the following values. Benzene, we are given 300 kgmol per hour. Then toluene, 200 kgmol per hour. Then hydrogen, 2200 kgmol per hour. Methane, 2167 kgmol per hour, and diphenyl is 9.8 kgmol per hour. This is the composition of reactor effluent. The fresh gas Fg is 667 kgmol per hour. Purge gas Pg is also 667 kgmol per hour, and recycle gas Rg is 3733 kgmol per hour. Now, if we split the reactor effluent into recycle, purge and then calculate the feed stream composition, then we get following values. Feed stream, fresh toluene will be equal to 300 kg mole per hour, because that is the production rate of benzene. Then recycled toluene, we assume complete recovery and recycle. So all of the unreacted toluene that is there, as we listed in previous thing, this toluene, unreacted toluene. Okay, this is reactor outlet composition, what we had listed before. Now we are writing the reactor inlet composition or the feed streams. Recycled toluene 200 kg mole per hour. Then fresh hydrogen, that will be 0.95 times the fresh gas, 633 kg mole per hour. Then recycled hydrogen, that will be 50% of the recycled gas, 0.5 into recycled gas, that is 1867 kg mole per hour. Then fresh methane, that like methane that enters as an impurity with fresh gas, that is fresh methane, that is equal to 5% of the gas, 33.3 kg mole per hour, or you can take only 33 for simplification. And recycle methane is 50% of the recycled gas, that is again 1867 kg mole per hour. The purge gas total is 667. So purge hydrogen is 334 kg mole per hour and purge methane is 333 kg mole per hour. And now we have to calculate the heat duties of each of these streams. Having done the material balance, we have to do the energy balance for the flow sheet. Now to do the energy balance, we have to look at the various temperatures that are involved in the flow sheet. Here you can see that the fresh gas is heated from 311 Kelvin to 895 Kelvin. The recycled gas is heated from 328 Kelvin to 895 Kelvin. The recycled toluene and diphenyl is heated from 391 Kelvin to 895 Kelvin, and the fresh toluene is heated from 298 Kelvin to 895 Kelvin. Now, if we have to calculate the heat duties on all the components like fresh hydrogen, recycle hydrogen, fresh methane, recycle methane, fresh toluene, recycle toluene, and benzene, so on and so forth, then we have to take into consideration the sensible heat plus the heat of phase change in case of toluene and benzene, and then the superheating of the vapor. Now, we shall see the heat duty of each of the stream. Okay. Now, let us say the heat duty of fresh toluene. Heat duty we denote by letter Q, fresh toluene. The liquid toluene has heat capacity of 156 joule per mole per Kelvin. It is heated from 298 to its boiling point, which is 110 degrees centigrade or 383 Kelvin. So this is a sensible heat. 300 kg mole is the feed plus the heat required for phase change, that is 32,000 joule per mole is the, or kilojoule per kilomole is the latent heat into 300 kilomole per hour plus the superheating of those 300 kilomoles of vapor. The heat capacity of vapor is 104 and the superheating is from the boiling point 383 to 895 Kelvin. So this is the total heat that is absorbed or that is required for heating fresh toluene. That comes out to be 29.55 gigajoule per hour. And similarly, we can calculate the heat duties on other streams. You must note that for recycled toluene, the temperature is 395 Kelvin, which is higher than the boiling point of pure toluene, which is 383 Kelvin, and this is due to the presence of diphenyl in the recycle stream. If you see the flow sheet that was there, you have the flow sheet indicates recycle of diphenyl, okay, here, and therefore, the temperature of the recycled toluene is slightly higher than the boiling point of toluene. So, that, but those minor things we are going to ignore in our calculation. Now, the heat duty on fresh hydrogen, Q, fresh hydrogen. The total moles of fresh hydrogen are 633.3 kilomole per hour into the latent heat 29 kilojoule per kilomole per Kelvin into the temperature. It is the fresh hydrogen is heated from 311 Kelvin to 895 Kelvin. So, this together comes out to be 10.72 gigajoule per hour. And now, I will give the other heat duties. You can calculate yourself. It is pretty straightforward. Recycle hydrogen 1867 kilomole per hour, 29 the heat capacity, and same temperatures 395, but from 328 Kelvin. This turns out to be 30.7 gigajoule per hour. Then the heat duty for fresh methane 33.3 kilomole per hour into the temperature 895 minus 311 into 36 the heat capacity 0.7 gigajoule per hour. Then Q for recycle methane 1867 molar flow rate, temperature 895 minus 328 into 36, 38.1 gigajoule per hour. Now, if you see the recycle heat load, recycle gas heat load, we have to sum up the heat load on hydrogen and methane. Recycle hydrogen like this heat load, okay, 30.7 plus 38.1, that turns out to be 68.8 gigajoule per hour. Then fresh gas load, fresh gas heat load, that will be 10.72, like basically this one. .72 plus 0.7, so 11.42 gigajoule per hour. Now, when we say net fresh feed heat duty, we have to add up the heat duty for fresh toluene, fresh hydrogen and fresh methane. Okay. Now, fresh toluene fresh hydrogen plus fresh methane, we just calculated 11.42 plus fresh toluene we calculated as 29.55. So, that we add here, this turns out to be 40.97 gigajoule per hour. So, that is the net fresh feed heat duty. Okay. Now, we have to calculate the heat given up during product cooling product cooling from 895 Kelvin to 311 Kelvin. So, this temperature range is same for all. First product, benzene, the total production rate is 300, the vapor heat capacity 82. From 895 it gets cooled to its saturation temperature 80 degrees centigrade or 353 Kelvin plus 300 into 30,000, that is the heat associated with phase change, heat liberated during phase change, plus the subcooling of the liquid, 300 into 135, that is liquid phase heat capacity of benzene, into 353 minus 311, that turns out to be 24.03 gigajoule per hour. Similarly, for toluene, 200 moles of toluene remain unreacted, the vapor phase heat capacity 104, from 895 to its saturation temperature 383, plus the phase change latent heat 200 into 32,000 plus 200 into 156, the latent heat in liquid phase, from saturation temperature to 311 Kelvin, this comes out to be 19.3 gigajoule per hour. And then for hydrogen, 2200 is the exit flow rate into 29 heat capacity into 895 minus 311, this is 37.26 gigajoule per hour. And for methane, it is 2167 into 36 into 895 minus 311, that is 45.56 gigajoule per hour. Now, the total heat given up by condensable components like toluene plus benzene, which ultimately end up in liquid phase, is 43.33 gigajoule per hour, and total heat given by hydrogen plus methane is 82.82 gigajoule per hour. Now, the heat given up during product cooling has to be distributed between fresh feed and recycle feed, that is liquid as well as gas feed, in proportion of the molar flows as the products form from the feed streams. This is the strategy we adopted while preparing the cost allocation diagram. In the previous lecture, we had the toluene feed fresh to recycle in the ratio 3:1. So, we split all the cost of the columns in the ratio 3:1. Here it is different. So, we have to first allocate the heat duties in proportion of molar flow rates and thereafter distribute the cost. So, that we do now. We have the total heat given up by liquid streams 43.33. Now, the fresh toluene is 300, recycled toluene is 200. Therefore, we have to distribute the heat duty in proportion 3:5 and 2:5 for the net fresh feed and recycle feed. So, that we do now. Liquid fresh feed heat duty like the component of product cooling heat duty associated with liquid fresh feed is 43.33 into 3/5, that is 26 gigajoule per hour. Then recycle heat duty or the fraction of product cooling heat duty allocated to recycle stream is 2 by 5 into 43 by 33, that is 17.33 gigajoule per hour. Similarly, the total gas feed is 667 of the fresh gas plus 3734 of recycle gas, and therefore the heat duty on cooling of the gas product component will be allocated to fresh stream and recycle stream in this proportion. The total heat duty as we calculated was 82.82 gigajoule per hour. So, that we are going to distribute now. .55 gigajoule per hour for the fresh feed and recycle feed .27 gigajoule per hour. And now with this we can prepare a heat duty table. Stream operation, heat load in gigajoule per hour and allocated cost. The three streams cost elements as we call them are gas recycle, liquid recycle, and fresh feed, and we just distributed the heat duties. Okay. The total gas recycle component of product cooling heat duty was 70.27. We just calculated here 70.27. This one. Okay. So that we list here. Liquid recycle was 17.33 and fresh feed was 38.55. Similarly, the fresh reactor feed heating, the gas recycle heating as we calculated here was 68.8. Then fresh gas for net fresh feed heating was 40.97. Okay. And then liquid recycle was 16.88. Okay. the total cost of product cooling, as we found in the cost allocation diagram, was $132,000. The total cost of reactor feed heating, as we found out in cost allocation diagram, was $297,000. And now we distribute these total quantities in proportion of the heat loads. Total heat load of product cooling is 126.15 gigajoule per hour. The total heat load on feed and recycle heating is 126.7 gigajoule per hour, and then we distribute accordingly the cost. It is just 70.27 divided by 126.15 into 132 is 73.5, like that. Similarly, here 68.8 divided by 126.7 into 297 is 161.3, and similarly the other cost 96.1. Now, having done this, we can now make a cost allocation diagram after we distribute the cost of reactor and stabilizer and benzene column as per the molar flow rates. Okay. So, the cost distribution of reactor, benzene column and stabilizer column. Stream: gas recycle, liquid recycle, that is toluene plus diphenyl, and fresh feed, this is hydrogen plus toluene plus methane as impurity, of course. Okay. The flow rates we have already calculated, you have to only sum them up. Gas recycle kilomole per hour 37, gas recycle 3733 kilomole per hour. Now, liquid recycle was 200 toluene. You can calculate with the K equivalent that is given the equilibrium quantity of diphenyl that is present, which is straightforward. We have done it in previous exercises. So, I am not going to tell here, it is left as an exercise, but I give the final answer, that is the equilibrium quantity of diphenyl in the present situation will be 9.8 kilomole per hour. So, 200 plus 9.8, that we approximately take as 210 moles. Then fresh hydrogen 633.3 or just 633 we can take, and the toluene, fresh toluene 300 moles, so 933. And then we distribute the cost of reactor, stabilizer and benzene column as per this. Reactor, the total cost was $200,000 distributed in proportion. The total molar flow rate, by the way, is 4876.3. You can approximately take 4876, okay, and then distribute the cost. 153, 8.6, 38.3, okay, or 153.1 to be exact. Then the stabilizer column. There is no recycles, gas recycle stream stabilizer, so that is 0, and the total $30,000 are distributed in proportion 18:12 to liquid recycle and fresh feed. Then benzene column, the total cost was $181,000 distributed as 109 and $72,000 in proportion of liquid recycle fresh feed. Now, having done this, we can now prepare the cost allocation diagram. The cost components are reactor, cost elements, everywhere cost element is gas recycle, net fresh feed, liquid recycle. I am showing now the products that come out of stabilizer H2CH4 and the product of benzene column benzene, and now we pick up all the numbers that are given in previous pages. Well, for reactor 153, 38, 9, for product cooling 74, 40, 18. These are adjusted to nearest integer in some cases. Gas recycle compression 110, 00. Gas recycle heating 161.300, or you can take just 161. Okay. Then net fresh feed heating, gas recycle 0, net fresh feed 96, liquid recycle 0, toluene recycle heating, gas recycle component 0, NFF 0, LR the liquid recycle 39.6, or you can take as 40 approximately. Benzene column, gas recycle 0, net fresh feed 72, liquid recycle 109, stabilizer, gas recycle 0, net fresh feed 12, and liquid recycle 18. Okay. And this completes the cost allocation diagram. However, we have not shown in this cost allocation diagram the losses that occur in the system. For example, what are the losses? Well, the first loss is that the loss of benzene in the purge stream. We have assumed a perfect split in flash drum. So, there is no loss of benzene and toluene through purge, but there is always some loss. Okay. Then the purge gas is itself a loss. Okay. That loss we can estimate. The total hydrogen in the purge is 333.3. So, if you multiply that by 8000 hours per year and the cost of hydrogen per kg multiplying by 2 for the molecular weight, you can estimate the exact loss of hydrogen and toluene and benzene. Okay, for toluene and benzene you will have to do the flash calculations which are available in any standard text like mass transfer operations by Trebal. Flash calculations will also be covered in the mass transfer operations course. Okay. So, this is how we prepare cost allocation diagram, and now this completes our tutorial as well as module on cost diagrams and quick screening of process alternatives.